All right, we're gonna get this started. They told us to start at noon, but we're just gonna start a little bit earlier. Can everybody hear me speaking? Good? Okay. Well, thanks for coming today to our talk on native Spark executors on Kubernetes, diving into a data lake. It's always good to see some familiar faces, so special thanks for all doing you guys that did some time for you. Okay, so before we get started, my name is Mariano Gonzalez. I work as an engineer for Jellyvision. I've been doing projects on the JVM for the past 15 years. My journey started around 2005, and over the last 5 years, I've been doing big data projects. And I have my co-presenter here.
Hi, I'm Grace. I've spent most of my professional career just figuring out good ways to ingest, store, transform data. But most importantly, we are just two people trying to learn about and share big data technologies and approaches.
So this is our agenda for today. At the very beginning, we are going to be doing some clarification, what you should be expecting to take out of this session. We're going to share a little bit about the motivation, why we decided to do this talk. We're going to be talking about some basic concepts about the data lake, how you define a data lake, challenges when you need to architect a data lake, maintaining it, all the governance around them. And finally, we're going to be presenting our solution, which is kind of a hybrid from different ideas that we took from different white papers. We're going to describe that. And obviously, we're going to be, everybody's here to see some code, so we're going to be showing some code. We want to make the session as interactive as possible, so feel free to stop us whenever we're showing code or whenever you have a question. Okay, so before we start, obviously, we're not going to be talking about the basics of Kubernetes. By quick showing your hands, who is familiar with Kubernetes? Okay, good. And what about Spark? Perfect. Okay, so we're not going to be talking about the basics here. We're going to be talking more about the integration between these two frameworks. And by this integration, we're going to be showing how to build data pipelines that allows you to ingest, process, and surface large amount of data and make it accessible for data science and data engineers. So our motivation, Grace and I, we've been working on big data projects over the last 4 years. And our relation with the Spark has been difficult, especially on the infrastructure side of the equation. At the very beginning, we started with EMR. EMR is the managed solution for a Hadoop installation in the AWS ecosystem. It's very great, and it was good because right from the beginning, they encourage you to separate or decouple storage from compute. Later, we evolved a little bit more our architecture, and we tried a Yarn installation. For those who are not familiar, Yarn is yet another resource negotiator, and it's a way for Spark to talk to an HDFS cluster or Hadoop cluster. All these solutions were nice pros and cons that we're going to be discussing. And later, we tried the standalone Databricks cluster, which is just the positive thing about that architecture is that you have your data co-located where your Spark executors are. So we're going to be talking about a little bit of pain and pros about these three solutions that we have experienced. But first, the term data lake was introduced in 2010 by the CTO at Pentaho. And if you think of a data warehouse as a bottle of water where the bottle is ready for drink, is packaged, structured, a data lake will be a body of water in a more natural state, where you receive different sources of different streams of data that are filling the data lake, and users just dive into, get some data, analyze it, do their POC or whatever, and move forward. So it's a place for taking just samples of it. The main characteristics of a data lake. First of all, they allow you to consolidate your infrastructure. Probably all we can agree that having a central place where you enforce your security policies is a good thing. So data lake allows you to do that. A central place is normally easy to manage and govern. A data lake also pretty much allows you to collect data at any scale. With this storage system, rather than file systems such as HDFS, Here we're going to be talking about the storage systems such as S3. You can store pretty much data at any scale, okay? And last, when you build a data lake, it also promotes the agility of your infrastructure. You can deploy batch data pipelines or streaming data pipelines that have different hardware requirements without changing your infrastructure. Okay. Any questions so far? Okay. So what's the difference, or one of the main difference between a data lake and a data warehouse? Well, a data lake allows you to, right from beginning, store any file in their native format. Meaning if you're ingesting Kafka, you can store directly Avro. Or if you're ingesting CSVs, JSON, a data lake is perfect to land the data there. Whereas a data warehouse, it's very likely that it will encourage you to first transform the data and then land it into your schema that you define. So flexibility when accessing data. For those who are familiar with BI tools such as Looker or Tableau, normally that brings some burden for developers because you need to clusterize the solution, you need operating ops side of the equation, so you need additional infrastructure. That's how this is a little bit more flexible when it comes to infrastructure against BI tools. And finally, a data lake enforces you the schema on read, whereas a data warehouse enforces you the schema on write. That means you need to prepare your data, you need to know how is your data gonna look like right from beginning. A data lake is more flexible in that regard. You can evolve your schema as you wish, and later, once your product or your idea is conceived, you just need to know what are you going to be pulling from the data lake. And so a data lake seems like a great idea. It's fantastic. I can land my data there. But how do I avoid this my data lake to become a data swamp? For that, there are the 4 pillars of data governance. And the first one is data catalog. When you land data into your data lake, you should know what data you're landing there, who is accessing, when it's being accessed, and also the data quality. What is this data, how is serving my company? And finally, data security. You want to enforce different policies for data scientists or data engineers. One might have read permissions, the other might have write permissions, or both. So these are the 4 pillars that you need to enforce in order to avoid the data swamp. So.
All right, so I'm going to talk a little bit about the challenges that Mariana and I faced when we went through our 3 different experiences of trying to manage a Spark cluster. So we identified 3 main challenges. The first one is the operational complexity of maintaining all the different parts of this data lake architecture. The second one is just the staticness of that architecture resulting in unextendable pipelines. And the third one is the complexity when trying to use this data lake and allowing people to ingest and access the large and fragmented data. So this first one, operational complexity. When we were using the other cluster management solutions, they're all very good. Like we just wanted to add an additional other solution to try to balance out different weaknesses. So the weaknesses or the challenges that we had, the first one was just the difficulty in resizing a cluster. So once you've built up your cluster and everything is good, trying to resize it, and then if you're a manager, it's like, oh, we need to change the size of that. It's extremely invasive. There's usually downtime, and it's a painful process. The next one is being forced to scale storage and compute at the same time. So even if you had a new job and you wanted to run something that was either compute intensive or just storage intensive, regardless, you have to just increase both of them at the same time. So it's kind of expensive and inefficient. Next is the being bound to a vendor-specific bundle, which can be a double-edged sword. First, that the bundle is supposed to be used to protect you, to help you, but sometimes when debugging and it's closed source, it's hard to look at the code itself because you can't look at it, it's closed source. Next is the lack of dynamic resource allocation. So we wanted something that would be easily spun up, spun down, prioritize something flexible that could work with our needs and kind of with the ebb and flow of our needs. And then Next, which is kind of like a really painful point, was the labyrinth of security that we had to set up. So most of the time you have Active Directory, which is run on Windows, Kerberos, which is run on Linux, and then Centrify that's supposed to tie the two together. And so navigating the different operating systems, trying to get them set up together while also connecting it to your data lake and to all your clusters can be like kind of scary and cause like a lot of pain. And just calling out two other things. For Spark, we had for the Spark standalone cluster, we had some difficulty in maintaining a cluster with different runtimes. So if you want a different version, usually you have to do something like patching the whole cluster itself. And then for Yarn, we had like a ton of different XML files and kind of got lost in them. So we wanted something that was straightforward and did not have too many things. So this next pain point, or next challenge, I guess, is the static architecture resulting in unextendable pipelines. So usually what happens for a company when they want to ingest data or they want to like set up some sort of data pipeline, they usually optimize it for either batch or streaming. It's usually batch. So they have something optimized to take like a large amount of data, manipulate it, and then store it, and then just repeat that over and over. But when you try to pivot to adding streaming to that, suddenly what you've optimized for batch doesn't necessarily make sense for streaming, and usually people just need to stand up a whole separate thing just because they don't really work well together. So we wanted something that from the get-go you could either go for streaming or go for batch, and that's totally fine, go back and forth. And then next is the user complexity in accessing the large and fragmented data. So this is 2 points. The first point is just the friction between like the users trying to like use the data that you're storing, and then the second one is like the developers trying to ingest the data in. So in terms of for the first one, frictions between users, we wanted to save the data lake, have the data stored in a certain way that allows users to be able to like easily query, like explore the data, do some sort of like whatever data exploration they wanted, while also like not taking down the cluster, having it be performant. But we also wanted to be able to have like ingest data from different sources, not just have it be like, oh, it needs to be only in Avro, or it needs to have this text schema to ingest into this database. We want it to be flexible, like to get someone up and running as fast as they can. So then we were talking about like, okay, like given all these challenges, what's like another like method to add into the fold, to add into these different like solutions that are available out there. So like Mariansha mentioned, we looked online, did some research on other possible solutions. The first one is this Medium article on data infrastructure from Airbnb from 2016. I'm mentioning the year because I wanted to, there's another slide and I'll show you the evolution of the infrastructure from there. But basically what you need to know about this is that there's like this idea of like two separate clusters. So there's the gold cluster and there's the silver cluster. And you cannot see that. So there's like that replication in between. So we found that to be really interesting. You have two clusters of data that's replicated across, and the benefits of that is the resiliency. So, oops. So for the gold cluster, if the gold cluster goes down and someone's trying to access data in the silver cluster in Spark, that's totally fine. No one's affected. They can still continue to run their jobs, run their computations. And similarly, if the silver cluster goes down, and then ingestion isn't stopped, like there's no like breaking of like the whole pipeline is down. So we like the idea of that sort of protection against resiliency, like flexibility. So next is a more recent one. This is the Databricks Delta Lake, 2018. They won like award for like most innovative software or something. But yeah, it's very innovative. It's very interesting. First, we like the fact that you can have both streaming and batch ingesting in at the same time. So there's no like completely separate batch workflow and completely separate streaming workflow. They both go through the same thing. And then we like the idea of the three different, I guess, tables. There's like this time it's reversed. It's bronze, silver, and gold. And you have that bronze table that does all the ingestion, so that you does all the ingestion. So anything that's from the outside, whatever schema, you can just save that automatically to the bronze section. And then there's this middle section, this silver section, that has a more refined, like maybe like not perfectly ready for like someone to do analysis on it, but maybe but kind of a little bit more cleaned. And then finally, we have that gold section, which is the like more beautiful, maybe aggregated data that's like ready for someone to go surface it, to like explore it and like run queries on it. So yeah, so our solution is kind of like a central place where engineers and data scientists can collaborate and run diverse workflows. So first we're using, talk about is about Kubernetes. We're using Kubernetes for this. We like the idea how you can use it to use cluster management and scaling and the flexibility that comes from that. We're using Spark to do data transformations. It's what people are kind of comfortable with, and it's also extremely powerful. We're using managed services. We put like Amazon here, but it could be anything. It's just our demo is in Amazon, but like managed Kubernetes and managed storage, basically, to like protect yourselves from trying to go through the labyrinth of configurations and all of that other pain. And then lastly, we're doing we're inspired by that bronze, silver, gold pipeline organization, and in our example we'll show you that we're going through that workflow, and it actually works quite nice. So Mariana will talk more about our solution.
So why we pick a storage system as our solution? Well, first of all, it's durable. You can typically expect 11 nines of availability, so that's pretty good. Scalable. Pretty much you can store like unlimited data on an S3 bucket or the equivalent in the Azure ecosystem. It's affordable. S3, the standard pricing is 1 cent per gigabyte. And secure. You can find granular access down to the object level. And integrated. Spark since 1.6 offers first-class citizen support for all the S3 APIs. So it seems like it was the right solution for us. But most importantly, it's a managed service. That means there is no operations burden, and developers can just develop without taking care of the infrastructure. When it comes to compute, why we pick AKS? Well, if you already are in the world of deploying containers, it will make sense to just start deploying your pipelines using Kubernetes. And since we are deploying containers, the runtime or developers are under control of the Docker images, meaning there is no longer the story, well, I need to patch the cluster, bump the runtime to Spark 2 point whatever, or I need to install a new Python egg and distribute it across all the clusters. No, that story is over because developers are deploying Docker containers, and the developers are normally in control of those images. And the best part is those runtimes are available from beginning. If you want to do Scala or Java or Python or R, the images are ready for you. And of course, it's another managed service. As S3, you don't need to take care, you just need to deploy your pipelines. So why we want to use Kubernetes as a cluster management? A data pipeline normally consists of a Kafka broker or any type of broker, the transformation layer, which in this case will be Spark, probably some visualization, and probably some queries to a database. So if you already have containerized all these applications, it makes sense to also containerize your data pipeline. So if you're already doing this, it's a good idea that you start also containerizing your data pipelines. If you start doing that, your resource sharing is going to be much better because you don't need a dedicated hardware for your data pipelines. Meaning, I don't know, if you have your Spark cluster sitting somewhere, like that pretty much most of the time might be doing nothing, it's going to consume your resources. Whereas if you have it in Kubernetes, the data pipelines will last the longer the job is. And another important thing is, for those who are familiar with Kubernetes, you can leverage all the Kubernetes APIs or ecosystem, meaning that you can have namespaces with dedicated quotas, meaning that if you define a namespace, this data pipeline can take X amount of resources. So you can define different namespaces and say, okay, this specific namespace will have certain quota or can request a specific amount of gigabytes. Any questions so far? Oh, okay. So actually, how does this work? It's actually pretty simple. If you're familiar with Kubernetes, Kubernetes has an scheduler API. So for those who are familiar with the Spark Submit is just a command that comes with any distro from Spark. And it's just a binary. So when the Spark Submit is executed, what it does is immediately calls the API scheduler from Kubernetes. So for those who are not familiar, the Spark driver is the link between your R, Scala, or Python code with the cluster. It's the thing that allows you to talk your code and the cluster and all the scheduling. So first of all, the Spark Submit is executed, a pod with the driver is created, and then the pod or the Spark driver schedule all the executors that you are requesting. We're going to be showing some code related to that if this is confusing. The only important thing here is like the Spark driver will remain alive until you kill it, so you can see all the logs from your job. The executors, or the pods where the executors are running, will be terminated immediately after the job is done. Okay. So what is so great about this solution, or what we consider that is great, is that compute and storage are completely decoupled. That means they can scale completely differently.
Yeah, I just want to talk a little bit more about kind of the compute advantages of the solution. So the first one, again, Kubernetes, you can go to any major cloud providers and have it be a managed service. The next part is kind of being able to customize more of your pipelines to something that's either compute intensive or storage intensive. And we have, spoiler, we have an example where we only really need to like scale up compute and not storage. And before we would be able to have done that. Next, the advantage is just minimizing the operational burden by being able to take advantage of like the flexibility of Kubernetes, spinning up a number of pods, scaling them down. They'll take care of themselves, which is really nice. And lastly, most importantly, is just instead of like the developers can now deploy using Docker containers. So there's no need to patch the cluster. If there's a particular version that they wanted to use, there was a particular like Spark version that they wanted to use, that's not the responsibility of the person managing the cluster. That's on the developers themselves. So if a new version came out and it broke their own thing, they're responsible for fixing their Docker container. And now both the developer can protect themselves and the person managing the cluster can protect themselves. Yeah, okay. In terms of the advantage of the storage solution, yeah, so storage is also managed. You can have one unified place for all your sources of data. So wherever you're hosting your storage, you can just look there instead of multiple different tables. And now you can ingest data in multiple different formats types because of the gold, silver, bronze layout. You can ingest like JSON in one area, and in like the bronze area, you can ingest Avro, you can ingest it this schema, that schema. That's fine. You can just store it there and then take care of it later in your silver section. And so this allows for like kind of a real-time and historical, like available data without that much change, and you can do like roll-up. You don't have to do like a roll-up process to like another storage technology. So we're actually going to show you an example of all of the things that we were talking about. Here's our example implementation. We wrote it in 3 different languages to show you the flexibility of like how anyone could kind of come in and write whatever they need and get out. There's no like, you need to write it in this framework, this specific thing. You can just, as long as it supports Spark, you're good to go. So we are taking, in our example, we're streaming data from Twitter. Just think of it like as just like our mock producer. We didn't want to like spin up like Kafka and like everything. So it's just this data coming in from Twitter. Then we have our Python stage, saving the data to the data lake. That's our bronze stage. Then from there, we have a transformation step in Scala, which is transforming the saved data within it, so it's the silver step. We have then something in R, pretending we're like a data scientist, trying to aggregate data. I want to manipulate the data in a way that is best for my model, so we have a last step in R for our gold section. And then lastly, we have like a layer of Zeppelin to visualize the data in the data lake. And then Mario will talk more about.
Okay, and this is just the final architecture diagram from the solution that Grace just talked about it. And the important part here to consider is that one might argue, well, you're duplicating data across different buckets, but we decided to pay that cost in order to have isolated process. So if any of the pipelines goes down, it won't affect the rest of the process. So that's why we decided it's okay to pay the cost of duplicating the data. But the data, even though it's duplicated, is in a different format. So in the first bucket on the very left side, you can see that we are landing JSON format directly to the raw bucket. So that pipeline is optimized to just land data as fast as possible. Okay, and we are not doing any transformation. We are just landing the raw data. So later we can do with the data whatever we want. The second step for the silver pipeline is where we start bringing a Parquet. Parquet is the most common columnar format, and there are other solutions such as Orc. But here is the first step, the silver bucket, where we do our first columnar transformation. And the third step is just the aggregation of this columnar format. We preserve Parquet as our aggregation format, but this is where the actual value of this data pipeline is. All the aggregations are going to be here. So the data in the silver bucket is pretty much a copy of the JSON that we have, but in a columnar format. And the very right side, the gold bucket, where the data analysts or data engineers are going to be consuming this table, these are aggregations. Okay? And later, as any pipeline, we have a visualization step, which in this case, we're going to be using Zeppelin. For those who are not familiar with Zeppelin, you can consider like pretty much as a Jupyter notebook with a little bit more feature rich, a little bit more rich in features, but it's pretty much a Jupyter installation. Both of them, as I mentioned earlier, all the processes will have at least one driver and n number of executors. Okay? Any question related to this? Good? Go forward. And finally, related to the buckets, it's a common misconception that a data lake will have a single bucket and we will dump everything into it. Well, that's actually not true. If you keep yourself organized, you can define these kind of like layers where you can define all my raw data goes to bronze, no transformations. All my silver data goes to like Parquet, where the first columnar format appears, and the gold bucket is where all the aggregations happen. So, any questions related to that? Oh, please.
Do you have an example of the Spark submits?
Yeah. We're going to be showing all this. This is the section for the demo, and we're going to be showing the different Spark submits in all flavors. R, Python, yes, we're going to be showing that. Any more questions? Yep, please.
So you mentioned you had the different buckets where you had your raw data, then parser data, then your structured data. So the raw data would be considered your source of truth.
Yes, correct. So the question was like, if the raw data can be considered the source of truth, the answer is yes. We never touch that. We just land data as fast as possible as we can, and it's pretty much immutable. We don't touch it at all.
What type of algorithms are you using for your data aggregation in terms of partitioning data together, piecing those things
Yeah,
together?
that's a very, very good question. And the answer is it all depends. If you're interested in getting aggregations for like 5 minutes, your partition will be like at the level of minutes.
Okay.
If you're interested in doing aggregations per day, your partition will be at the year, month, and day. So it pretty much depends on you, how you want to aggregate the data. We're going to be showing something related to that.
And then in terms of like data segmentation, are you doing it at the gold level or are you doing it at the bronze level?
We're doing it at the silver and the gold.
Okay.
At the silver, we're partitioning by date.
Okay.
And at the gold level, we're partitioning by minute. But it's like, that's pretty much open for you.
Okay.
Yeah. Did I answer the question?
Kind of, what I mean is that in terms of as each date changes state from, let's say, CSV or JSON to the format in the Parquet or Avro in the silver state, how are you like, is there some other downstream systems that are listening to those state changes so they can respond quickly for them, or you're concerned about just landing data in the
Yeah, the latter.
Okay.
All right. Okay.
Okay. Okay. So if you wanted to follow along, I think GitHub is down, but if you, in the future, you wanted to look back, then you can visit this page. So yeah, you came here to see some code. We will show you some code. right now we have a managed Kubernetes cluster in the cloud at the Chicago Cloud Conference, and we're going to run a pipeline, or set up a pipeline for that. So just to show you the code for that, this is all we did to set up a cluster for Chicago Cloud Conference for EKS. Another thing, just to like show you exactly what we did, so you can like go home and try it out yourself. Other things we did besides setting up the cluster beforehand was setting up the different roles and setting up admin and creating a service account for Spark, creating a role for it, and just like saying that you can edit it. So that's what's running right now. Okay, so more in depth on the Bronze pipeline. Right now, this Bronze pipeline has kind of two parts. One part is our fake data source, our Twitter producer. And the second part is the more important one. This is the actual Spark job, a Spark streaming job in Kubernetes. And note that this is just the normal Spark streaming. It's not structured Spark, which is what Mariana will talk about later. But what the Twitter producer does is it listens to data from like hashtags from Twitter using the Twitter streaming API, and it's taking that and sending each tweet over a TCP connection, which the Spark consumer is consuming from, and the Spark consumer will then save it into the Bronze bucket. So that's that setup, and I'll walk you through the code for that. Okay. So the first part, I'm going to show you the manifest for Kubernetes. This is your normal looking service for like a manifest file for Kubernetes. Name is Twitter producer. The interesting part here is that we're not actually just sending code, we're not like uploading code in our example. We have it all in this in this Docker container that we're controlling. And so if something is like, so all we would be submitting to our cluster or to our Kubernetes setup is just this manifest. So that's quite nice. And then we have just our normal, our secrets, our keys, and then, so we needed a lot of data so that people wouldn't wait. And so we have to pick the most popular hashtag on Twitter, which is this one. But don't think too much about that. It's just, yeah, so we're just listening to this tweets about this. All right, so moving on. So now you have that manifest file, and then to actually, all right, well, okay, we'll just continue. All right, so we have that manifest file, and to actually apply that into our cluster, we're taking these, we're using this fancy command, which is just like substituting environment variables, and then we're just applying it, and that's all it takes. I'll show you the code itself so you kind of know like what that example looks like. Okay, so we're starting from here. This is the TCP connection server that I told you about. We're just setting up the socket server. This is a blocking connection, so basically what it means is that it's waiting for someone else to listen to it, and then it'll just start sending tweets over. And then the main part is here, this streamer. So it's taking in this TCP connection, and then it's just sending the tweets to Spark. We did some a little bit of split manipulation to pretend that we had like a great data stream, and so we do split so that each message is like a separate tweet. And then that's it for the producer. So I'll launch the producer right now too. So here.
It's just important to mention that the producer is just a mock of the Kafka broker, so itself is not a Spark job. It's just a standard Python app.
Yeah. So I ran this. So it's applied the Kubernetes manifest. And then don't look at these other things. Just look at this one. It's a spoiler. So we're looking at this. So you see that's all we need to do. We just need to apply the manifest. And if you wanted to look at the logs here. So it's waiting for the connection so it's waiting for a connection so that it can start sending tweets through. So then we have, so that was the producer, and then this is the consumer. This is this, actually, I'm gonna start here. This is the consumer that's going to take the data, that's a Spark streaming job, and save that into our bucket. So you came here to figure out how to run a native Spark executor on Kubernetes. The key part are these parameters. Just these different parameters. You have your normal Spark submit, you have your just the Spark master, memory, and configurations. But the key part is just this, setting your Docker container and also just saying that it's like setting everything up as Spark. And that's honestly it. The rest of these are our
They have a question.
oh, question? Hi.
Hi, so as far as the POG spec that you had in the manifest,
Mhm.
you said no resource limits at
Yeah.
all.
Yeah.
Correct. Yeah, we have that's the one that we didn't set up any resource. Yeah, good catch.
Yeah, that's true. Maybe in the next version, we'll do that.
Since it wasn't a Spark submit or Spark job, we didn't pay much of that attention. If it crashes, yeah, click it. Well, yeah, good catch.
Yeah. Okay. So yeah, so it's just running the Spark consumer.py, and then the secret is kind of in these configurations. So in terms of the code itself, so yeah, the first thing we're doing here is setting up the streaming context. That's like the configurations to set up, so it's being able to talk to Spark and it can like get where it needs to go. So yeah, so this is like standard. You're setting a master, you're setting in the name. This is kind of interesting, so I want to clarify that we're not using Hadoop at all, but we need this, and then this is in org Apache Hadoop. So I just want to clarify that. So the key part for us to be able to move data from our Spark streaming into our storage system is, in this case, this S3A file system. You might have heard S3N. To connect to AWS, this is just like a more recent version. And then more interestingly, we have this checkpoint here that allows us to kind of save our place, so that if you need to, if things goes down, you need to start it back up and rerun it, it'll continue on where it left off.
Yeah, go ahead.
That state, where is that saved?
Where is that state store?
That checkpoint, yes.
Yeah, in this case, or for this case, if you were running locally, we'll create the folder at your wherever you're running the code. And if in case of EKS, it's a persistent volume located on the DBS. Very good catch, too.
Yeah, that's a very
good questions there.
important note. Yeah, so that's quite nice. So that part was just setting it up, and then the next part is listening to that TCP stream, and then here and in this section we're processing the tweets, and that's just this line. So we're listening to the data, we're like setting it up to be able to write it through Spark, and then we just write it like this, and it's just one line to save it. I will talk about what reverse current time millis means, or why we have that here. It is what it sounds like. It is the reverse of the current time millis, but I'll explain more of that, of like why we have that later. Okay. So.
You show the bucket, the raw bucket, yeah, show the bucket.
Yeah. So here's our bucket. We're going to put some data in there. Okay. So in this section, we're running that Spark submit with all the different configurations, all of that set up. In our Kubernetes section, we have a watch on here, so you can see this looks kind of like, it's like a pending, but you can see that the container is being created. It knew to like set up its driver, and knew to set up 2 executors, and those are going to be writing, and those are going to be like ingesting from the producer and writing it into S3. So here, want to look at the logs for it. So here it's listening data. This has this checkpoint, it's saving, and then you can see.
Hey.
Oh, it's today.
Just let it run.
So you can see it here. So you can see like all the data being saved. Yeah, the reverse millis, we have it because we wanted to bring the less precise digits to the front so that in terms of search for, in this case, like S3, it's easier instead of trying to search like 1, 5, 6, 3 and like looking over and over. You can now search like 7 and then you can like look here. So that's why we have the reverse millis.
It's a quite useful technique that many people use when writing to S3. So the key is it doesn't match many buckets. So if you start with the less natural or the less significant digit, the chances that you match at the beginning are less, rather than if you match with 1, 5, which is all the time millis that start with.
Yep, so here's our consumer.
All right. So Grace talked a little bit about all the ingestion process and how we're landing data. And related to the silver pipeline is just a Scala job that is going to be taking everything from the raw bucket or the bronze bucket and dumping it into the silver bucket and doing some parquet transformation. So obviously, since this is a transformation step, the heavy lifting is going to be at the transformation step. So I'm going to just show you very, very quick what we did for this. Since we're using Scala or Java, it's a little bit more compact than Python. I don't want to say superior. And here we have our transformation step. So for this, let me explain a little bit. First, we have an ETL definition. Here we're leveraging, it's called a Spark Data framework, which is a nice wrapper on top of structured streaming. They provide convenient APIs. So it's very, very easy to define your, let's say, ETL definition. And what's an ETL definition? You just define from where are you going to be reading, what's the step or the function that you're going to apply for the transformation, and where are you going to be syncing to. So our first step is, or our reading source is just this. We're going to be reading in JSON format from S3. And here we have like the data, exactly what we were mentioning. Here will be the partitioning and the file. So if we go here, oh yeah, sorry, I have it run. Sorry, before we're on it, and the writer, where are we going to be syncing the data, which is just the right part. Okay, now the interesting part here is all the transformation. So bear with me with this. Since we are receiving a JSON object or we're landing directly into JSON files, we're going to be leveraging a couple of Spark SQL functions. So basically, this getJSON object allows you to explode the object. So you can execute pretty much JSON path operations on the JSON object. So here we're just extracting the time in milliseconds, the extended tweet. There are some cases, the streaming API from Twitter, some cases they don't offer the extended tweet. And we're using the extended tweet because the hashtags are normally contained here. We're also extracting the text and the user. And with that, we're just transforming, for doing the partitioning, we're transforming the milliseconds into a date. And later, we're also extracting from the user, which is another JSON object, we're extracting the location, and finally, the full text. These are just columns that are being added dynamically to our initial data frame. That was just this select question. Yeah.
So you construct the data frame from a query standpoint. You're not necessarily going to know the size. So when you do a Spark submit, and when you specify the amount of capacity that you have?
Not the amount of data that we're going to be retrieving, but the compute power that we're going to be using.
But you're not going to know. Well, I guess the question is, do you have a rough average of what that is to know that? I'm sorry. Do you give yourself buffer to account for any large data set? I'm assuming.
Yeah, the interesting part of the data frames, good question also, is that they are lazy evaluated. So all these operate, yeah, exactly, that answers your question, okay. And later on, we just apply a regex. So we examine all the tweet and we extract all the words located to the right of the hashtag symbol, and we get a CSV value. Yes, and now going to the lazy evaluated nature of the data frames. Just when you have a terminator operator is when all the DAG graph is evaluated. So, and a terminator operator could be considered a group by or write by. So when you get all the data, I know which specifically I'm gonna be writing, not everything at once. Okay? And obviously with the executor, it is partition and each executor takes a task. Okay, so now we're gonna be running the transformer. From this side. As I mentioned previously, this is just gonna move the data from bronze into silver. Let's query this guy. So here we have our containers. We have two for the Scala project that is here. So we're just gonna very quick query the logs for this guy. Okay, so the process of moving data just started, and let's see if we get something very quick here. All right, so probably this will answer your question. Here is the created date. This is the first partition. You won't see this date reflected as part of the data frame. It's explicit part of the partitioning, how S3 lays out. And this is just if you're going to be doing some Hive transformation, some metadata that the Spark adds on top of it. It's a very common setup to also have the Hive for query purposes, not for inserting though. Okay, so we have two of the pipelines running. And I'm just gonna fire before we jump into the code, I'm just gonna fire the gold pipeline. Oh yeah, sorry. And we will jump into the code very quick. All right, so we have pretty much, let's see. All right, so we have pretty much all our pods running, and just a very quick difference between one and the other. So this is the transformer. This looks pretty similar to the initial Python submit. The only things that are changing here is just the image that we're going to be using. Instead of using the Python image, we're going to be using the Scala or JVM image. And something interesting to notice here is that the driver and executor have the same memory for the Python and transformer job. However, since we're going to be doing some aggregations, normally aggregations tend to be a little bit more expensive in terms of resources, and it seems that R is also compute intense. So where's the run aggregator? Oh, sorry. This is pretty much the same submit, but please keep in mind that here we're building a more heavy or a more, instead of having small executors, two small executors of 4 GBs each, we're building a bigger executor of 6 gigabytes, and it's just a single one. So this is also very important to the first point that we were mentioning at the beginning. We're deploying resources that are pretty intense when it comes to getting data, but we also have a pipeline that is more compute intense. Yeah, go. Yeah, question? What? Sorry, I didn't hear you. Yeah, go for it. Okay, and just the R program. So let's examine the R program very quick. You're gonna be surprised how similar it looks to Scala code or Java code. So first is the standard thing that you just have to do for every single Spark program. You define your Spark home, Sorry, I didn't talk about it. But the Spark Home normally, or sorry, the Spark Master, this looks like the standard Kubernetes URL. So here is the cluster. So this is pretty much the URL that matches what we have here. So this URL pretty much is like you can get it from EKS or get it from here. And when it comes to instances, here are our 5. We didn't want to recreate the cluster in front of you because it's just 20 minutes of doing nothing. We could have done it at the very beginning. You can see that they've been running since yesterday. We just wanted to have it ready for you guys. So there's not much to look here other than that. So let's go back to our logs. So this is our aggregator, and this is the one that is running. And if everything goes well, or if we give it enough time, we should see. Okay, and here you can see our partitioning by the grain size of 5 minutes. So that's what I was trying to mention. Like, it all depends to the strategy that you are doing, okay, and how you want your data. Okay, so this is pretty much all our pipeline, but we need to visualize it, the data, right? This will be worthless if nobody can see it, right? So for this, any questions so far? Yeah, go for it.
What do you do with the small files?
Sorry?
Small files? You get a lot of small files.
Oh, yeah, that's it. Yeah. Thankfully, that's not a problem like is in HDFS, where you have a block storage and the rest of the file is gone. For S3, it's not that expensive to have small files and aggregate them later. Whereas when you were in HDFS, that's definitely a problem. Does that make sense?
We have a problem with S3.
Mm-hmm.
There's a lot of small files and the read takes a lot of time. Like we get timeout exception.
We can talk about it. I have some, yeah, let's sync up after that, yeah.
I'm gonna say that you can set Spark to set the file size to
Yeah, that-
250 gigabytes or however size you want. And then as it's writing out the parquets and avros, you can get it into that precise size file up to a point. But it'll make sure it fills out before it's the next file.
Okay, so I also deployed the Zeppelin server right before we started the presentation. So here's our our pod, the Zeppelin server. We have all our pipelines running. So in order to make available the UI from Zeppelin, we just need to forward the port very quick. All right. And this is our visualization tool. So we have also a notebook ready for you. So we're, and just bear with me. So we're just gonna import the notebook that we have, that we prepared for this class. All right. So the very first step is, as any notebook environment, exactly what we've been doing for the rest of the 4 apps. And we're gonna define the number of instances, the file system that is gonna be our backend, and I'm gonna do something that I shouldn't be doing. I'm gonna paste some credentials there.
He'll delete them later.
Yeah.
Don't worry about it.
There are obviously way better ways of doing this, right? Such as injecting the container with the right credentials. So we're gonna just run this guy. So this is where our last step happens. So any streaming job or Spark streaming job normally adds a window column with the window from where to where was the window. So since we're not interested in plotting that column, we're just gonna drop it. Same here, we're gonna group by hashtags, so later we can do the count. And let's see how, and later with that data frame, we're just gonna register the data frame as a temp table. All right, so fingers crossed here. This is step lower, and sometimes it takes a little bit longer. But just wanted to let you know that the end goal is to get like a graph pretty much similar to this. Any questions so far related? Yes, please.
So did you guys consider just running Spark on a cloud era or a Hadoop distribution of any kind for Kubernetes, any reason?
Yeah, we did that, and our experience was terrible. And the reason why is because they sold us the idea it was gonna be just a single click. That's not the true in reality. And so yeah, our experience was not as nice as you would imagine. So, but we just talk about all the advantages of like not doing a vendor specific thing. Yes.
Just curious, you referenced Databricks architecture, and I know from a backend storage standpoint, they have some memory-based file store, and I'm curious, why do you continue having your aggregations go to S3 instead of leveraging that store, or unless they're not using Databricks as Spark solution, using standard.
So the question is, why are we not using a file system rather than an object system, an object storage system?
Either an object storage system or something that's memory backed, primarily just primary.
Yeah, that's also a very, very good question. And if you come from the Yarn architecture, normally when you deploy your EC2 instances, you also specify right off the bat at the very beginning the size of the EBS volume that you're going to be mounting, right? Increasing that is kind of difficult, right? Normally, either you deploy a complete new EC2 instance, which might not be needed because you might be just requiring more storage. So your compute might be completely wasted because you just need more storage. So that's the whole motivation why we're using a storage system. Simply for like decoupling storage from compute and scale differently. And so yeah, so this is just our final product. So this morning we can see that the people is tweeting about Russia, gay race, and blah, blah, blah. And yeah, so we went through the whole demo here. And just to start wrapping up here. This is the pipeline that I was talking related to the transformation. This is just the gold pipeline. Sorry, I forgot to mention more about this code. It's very, very straightforward. You build your Spark session, set the login label, exactly the same flags that you set for Scala, Python. Yeah, question? Okay. No, and since we're going to be reading from a columnar format, we need to specify our schema upfront. Again, we just define the read, or the source that we're going to be reading. And here is the interesting part. First of all, we convert the timestamp again from milliseconds to seconds because the windowing operation of structured streaming requires seconds rather than milliseconds. This is also a very, very, very cool feature from structured streaming is with watermark. So all the events that come later after 10 minutes will be discarded. So you can guarantee that you will get the latest here in your S3 bucket. And the size of the window, again, very, very, very straightforward. And the final, in order to do the partitioning, this lit operator creates a column that is just going to fill by 5 minutes aggregations. And finally, where are we syncing? Now, so, and this is our visualization step. This will be the last part of the pipeline. And just to wrap up the future work, running this bash script is kind of nasty. It's difficult to maintain. There are a lot of properties to set, and not many people like that. Thankfully, the very smart people at Google are building the Spark operator. So if you're familiar with Kubernetes ETL, it's very, very easy to extend the commands and create your own commands. So that's what the Google folks are doing. They are just extending the Kubernetes CTL and creating something called the Spark CTL. And that Spark CTL will allow you to interact more easily with via manifest file with Kubernetes. Instead of having these difficult to maintain, difficult to read bash scripts, the Spark operator will leverage all that. And it will give you access to state, metrics, retries. There might be cases where your pods are dying and you want to retry them. So all that work is going to be done by the Spark operator. It's a Golang project. For those who like Golang, it's a nice way to get into it. And here's pretty much the roadmap, what they are planning to do: support multiple Spark versions, priority queues for those who will come from the Yarn ecosystem. Probably you missed that. Spark CTL as a plugin for kubectl, and it will be supported by Spark 3.0. All right. So, any questions?
That was awesome.
Thank you. Yeah, we have some minutes. Yeah, go ahead.
The languages that you choose, did you choose them just to show the variety, or did you choose them because they are at the best of transformation, storing the raw data, and aggregation?
I think it was for fun.
It was for fun. It was just to
However,
show
we I have something to say. We come from my JVM. Well, not you, but I come more from my JVM world, and I find more natural to use plain Spark JVM or Scala than R. So, and also the motivation for doing the aggregation, we were planning to bring some pandas and NumPy, but we didn't have time at the very end because, and you know, the transition between a pandas data frame and a Spark data frame is kind of easy now with the Apache Arrow. So we were planning to do something in that regard, like, and that's why we pick R for the aggregation part, like planning to leverage on some NumPy or any type of that aggregation functionality. We didn't do it. So with that being, yeah, no actual, we use like Python, R, Scala. Good. Obviously the Docker repo, sorry, our code publish all those images. They are very similar. So this can be generated by the Spark tool. By the binaries that the Spark ships with, and we just tweak a little bit to ship it with our jars and a couple of libraries that we were interested in, which is obviously the SDK, the AWS SDK, and the Hadoop AWS. And the Python one, we just ended up adding a couple of libraries that we were going to need for our project. And the R one is pretty much the same one. Yeah.
The way that I understood this portal was that you had an idea of the data set and how it was structured to put this in your data lake. But if you did not have an idea of what you're pushing into your data lake, what would you change in the solution? I'm assuming you would have some type of exploratory layer, but the technology.
Yeah. On that regard, I feel that having the ability of having the raw pipeline is fantastic because that's your raw data. So your process can evolve. If your raw data is always there, you have it there and it's not transformed, you can evolve your transformations. So I think I wouldn't change anything because the project is already set up for that. If I need to modify, I just modify the transformation thing and the ingestion continues pretty much there. So yeah, I feel that we're good on that. Yep.
So in terms of data lake, how do you manage your data lake manually or as automate tools?
No, well, Grace talked about it. Like the two of them are managed services, so we are just deploying containers. So we just need to see if our container was deployed. But pretty much EKS is a managed service, S3 is a managed service, and those are the two pieces of infrastructure that we're dealing with. So, yeah.